Two parallel plates having charges of equal magnitude but opposite sign are separated by 12 centimeters. Each plate has a surface charge density of 36.0 nanocoulombs per meter squared. Proton is released from rest at the positive plate. Determine A, the potential difference between the plates. B, the kinetic energy of the proton when it reaches the negative plate. C, the speed of the proton just before it strikes the negative plate. D, the acceleration of the proton. And E, the force on the proton. F, from the force, find the magnitude of the electric field and show that it is equal to the electric field found from the charge densities on the plates.
Got a little ahead of me there. We got the, we're looking for the change potential between the plates. We're looking for the kinetic energy of the proton if we're taking a proton and letting it go at the positive plate. Velocity final of the proton, D.
Acceleration.
Acceleration. E.
Force on the proton.
And
Magnitude of the electric field.
the electric field. Good. There's plenty of stuff there. The symbol for surface charge density is like
A circle thing
Well said.
yeah. This one has a name. Bill, what is it? It is not phi, unfortunately. Grofstetter? I know she's not here. Bailey.
Lowercase.
Yes, it is lowercase. We're getting closer. Lowercase, very different.
Sigma?
Lowercase sigma. If we have an electric field that is oriented like this, the plate on the left is the positive or negative plate. Positive. The positive plate. So we have the positive plate on the left, the negative plate on the right. We're going to release a proton from the positive plate. So we're trying to figure out the electric potential difference that exists between the two plates. That's how we're going to start. Bless you. Miller, thoughts? Electric potential difference between the two plates.
Does delta V equal K Q over R?
Delta V equals KQ over R under certain circumstances, but not for this particular problem. What is that for? Look. This is for a point charge. Okay? So this would be the electric potential difference between a point infinitely far away and a point R distance from a point charge. Not what we have in this particular case. Electric potential difference. Gary? Vasily?
Negative integral from A to B of E dot ds.
True. But we actually know it in this case. I told you last time that you have to have this equation memorized and you need to know how to derive it.
ED, negative.
The electric field equals negative E times D.
You mean the potential difference?
I'm sorry, I think that doesn't make any sense. The electric potential difference equals negative E D. Under what circumstances is this equation true? Jenkins?
Constant electric.
In a constant electric field, which is what we have here. All right. So we have D, we need the electric field. How are we going to figure out the electric field that exists between these two parallel plates? Catherine.
Well, you have the surface charge density.
True.
So,
I agree, we have the surface charge density. Jenkins.
We're going to use Gauss's law.
We are going to use Gauss's law. We're going to start with a singly positively charged, very large plate. We're going to start with Gauss's law. Gauss's law. Basil.
Do you want to draw the Gaussian surface first?
Sure, we'll do the Gaussian surface first. What's the shape of the Gaussian surface, sir?
Isn't it a horizontal cylinder?
A horizontal cylinder, sure. We're going to draw a horizontal cylinder. I will illustrate it like such. So we have one end that looks like this. We have another end that looks like this. And it looks like that. Great, that is our Gaussian surface, which is a cylinder. Great. Gauss's law, Nitish,
Case B, with a subscript of B.
which stands for what?
Electric flux.
Good, is equal to?
Surface integral of E naught dA is equal to Qn over E naught.
Good. Walk me through the derivation of the electric field which exists around this positive charge plate left.
You repeat the question?
Sure.
We're gonna have EA equals QN over the symbol.
Yeah, there's a bunch of stuff in between there, and I need to know what it is and why.
So closed surface integral of E dA cosine 0.
Okay, so we have E dA times a cosine. Now, I'm not going to put 0 just yet. I'm going to put theta. I agree, it is 0, but for what?
For the cylinder, like not the size, just like the cylinder.
Okay, that's actually, you've got it reversed. Okay, dA for this end, class, point, please. dA is this way. dA for this end, please. This way. So notice that for the ends, theta is equal to 0 degrees. What about for the side? Okay, for the side. So here we go. Class, how about right here on the side? Please point in the direction. Directly toward you, right? What about the top? Pointed up, the bottom, pointed down. Every time, class, the angle then is 90 degrees. So notice that the cosine of 90 degrees is 0. Therefore, we only have the electric flux for the two ends. And we now have, that's E dA, because the cosine of 0 is 1. Good. Keep going, Vlad.
Alright, well we can take we can take the E out,
Because
it's constant.
it's constant. Notice at that Gaussian surface, at the end, it is constant. Good.
And then it's just gonna be EA.
But the area of what?
On the area of the Gaussian surface.
That's okay, not quite understanding. What is this the area of? I agree the Gaussian surface, but I need more specifically here. Is that? Sorry, say again?
Cylinder
Want to be clear here. Say it again.
and of the Gaussian surface.
It's not clear to me. Did he say it?
I don't know.
I don't know either. Miller?
Two ends.
Ends. I don't know, I couldn't tell whether it's an S or not, right? It's the two ends, both ends of the Gaussian cylinder. So what I'm going to do here is I'm going to put 2 times the area of a single end to better identify that. What about the charge inside the Gaussian surface? What do we do with that, please? Hamza.
What you can do, you have the surface area charge or density.
He's got all the words in the wrong order. Surface area charge density.
Yeah.
Or the circle with the line.
Which equals Q over A, which equals like Qn over A of the end.
Over the area of a single end. Therefore, the charge inside the Gaussian surface, this charge right here, is equal to the surface charge density times the area of a single end. Therefore, we get the surface charge density times the area of an end divided by the permittivity of free space. Everyone brought the area of the end to the party.
We'll send Michael. Wait, you're expert?
Therefore, the electric field that exists all around this single positively charged plate is equal to the surface charge density divided by 2 times E naught. We're looking for the electric field total that exists between the two plates. Emily, what's that equal to?
Would we have to, it would be 2 times that.
It's 2 times the electric field from one of them. So what I'm going to do here is I'm just going to make it obvious. The electric field that exists from the positive plate plus the electric field that exists from the negative plate, or 2 times the surface charge density divided by 2 E naught. In other words, the electric field total is equal to the surface charge density divided by E naught. We don't necessarily have to find that to figure out part A, but I want to find it to prove something a little bit later. So the electric field then is equal to 3.6 or 36.0 times 10 to the welcome Dorstetter.
Pass. Your zone office will finish.
You're her path.
Yes.
Impressive. Thank you.
This is right when I say I gotta walk that way anyhow.
All right, good.
So she's fine.
Thank you. So we have nanocoulombs times 10 to the negative what, Bailey? Times 10 to the negative 9 divided by E naught, which is 8.85 times 10 to the negative 12. So the electric field total that exists between the two is?
Um, 4067. You want to do 7661.
That's fine. So we'll say 4,070 watt for the dimensions on the electric field. Hillary, newtons per coulomb or what? Mohit? It has volts in it, true. Who's got it for me? What's the other one? Sarah Jane Jones.
Volts per minute. Volts per meter.
Volts per meter. They are one and the same thing. Okay. Actually, that wasn't an answer, but that's fine. So now the electric potential difference, which is equal to negative ED, is equal to negative of the 47.8 times D, which is 12 centimeters. So we get, please.
488.14.
And that's in volts. And they don't actually identify a direction at all. So when I give my answer, I would give a positive answer, which is 488 volts with sig figs. Again, because they don't really specify any sort of direction. So whether it's negative or positive is pretty much irrelevant at this point. B. Yes, now we start part B. Part B. This is to find the kinetic energy just before reaching the negative plate. What do we use to figure this out, Mr. P? General strategy.
You use conservation of energy.
Conservation of energy, because?
There is no friction and no force applied.
Great. Conservation of mechanical energy. Do I need to draw my zero line, Mr. Potterell?
No. I mean, yeah. I mean, it can't hurt.
Please answer the question with something other than it can't hurt, Catherine.
That would be because for atomic particles, gravitational potential.
For atomic particles, we don't need gravitational potential energy. It is negligible. So we have mechanical energy initial. Nick, what sort of mechanical energy does the object start with?
Electrical potential energy.
Electrical potential energy. PE sub ELE initial. Anything else?
No.
No springs, no kinetic energy. Good. Equals.
Kinetic energy and potential energy.
Plus the electric potential energy final. Great, let's rearrange it. We get electric potential energy final minus the electric potential energy initial is equal to the negative of the kinetic energy final. In other words, the change in electric potential energy is equal to the negative kinetic energy final. What is the change in electric potential energy equal to? Nitish?
Q times the change times the voltage.
Times the electric potential difference or the voltage, which is equal to negative 1/2 mv final squared. Actually, we're just trying to figure out the kinetic energy final. That's the answer. Then, of course, we're going to figure out the velocity final. It's kind of weird, but that's fine. So the negative kinetic energy final, or do they ask for the, what specifically, do they ask for the change in kinetic energy or the kinetic energy of the proton when it reaches the negative plate? So that would be the kinetic energy final is just equal to negative Q delta V. Charge on a proton. Tim? No, let's try again, John.
Oh, come on, guys.
Charge on a proton. Class, do you have to have it memorized?
Yes.
No.
Oh.
Should you?
Yes.
Yes.
Come on.
Matt.
1.60 times 10 to the negative 19.
Times the electric potential difference, which is what, Bill?
488.14.
Kinetic energy final.
Negative 7.81 times 10 to the negative 17.
Joules. I'm confused. Can you have negative kinetic energy? Can the mass of the object be negative?
No.
Can the velocity be negative?
Yes.
What? It's squared. Can you have negative kinetic energy?
No.
No. Sierra, help me out.
We should have carried over the negative from like part of it. We took off the negative because it didn't like ask for the direction.
Right. How do we know the electric potential difference is negative? I agree we need the negative there, but I need to know how it is we know it is negative when we go from the positive to the negative plate. Zilla.
I mean, you had potential to move towards the negative when you started, and now you ended. I mean, it's just kind of like with the way the arrows are. I mean, you started with it, you didn't have anything.
I'd like more than it's just kind of like the way the arrows are. I'm sorry, I need more. Gary.
I think it decreases along the electric field.
Remember, the electric potential decreases in the direction of the electric field. So as we go in the direction of the electric field, that electric potential goes down. Therefore, it is going to be a negative. So we end up with a positive for our kinetic energy final. That's equal to 1/2 mv final squared. So kinetic energy final, we can solve for the velocity final, which is equal kinetic energy final divided by mass multiplied by 2, the square root of 7.81 times 10 to the negative 17. That times 2 divided by the mass of a proton. Mass of a proton, please. Zach? Times 10 to the negative 27, thank you, the square root of that, the velocity final of the proton.
3.056 times 10 to the 4
Times 10 to the 4th
meters
meters per second. Independent confirmation of that number, please.
Are you just setting up AD right now? It's wrong.
What I'll say is it doesn't match what I've got.
Oh, wait, hold on. There's a little point ones in there. It's like 0.0583.
How about we get somebody else to help us out here as well?
30,583.
Yeah, that's what I got.
30,580.
Which would be times 10 to the 5th, right?
305,000.
1, 2, 3, 4.
Okay, it's just
The six should
a
be
different number every time.
No, I just missed it.
Somebody else say something.
Times 10 to the 5th?
I have to.
That's what I got. I'm sure that's it.
So ridiculous.
3.06 times 10
Oh,
to
is
the
that a
fifth.
17 or a 19 up there?
That's a 7. I got it.
Alright.
So we have the velocity final. Next, part D asks for the acceleration. How are we going to figure out the acceleration? Who's got an idea? Figure out the acceleration? Travis?
UAMs?
Just UAM. If you look, we've got just uniformly accelerated motion. So we could say, what do we know? Velocity final, velocity initial, and displacement. So we could say velocity final squared equals velocity initial squared plus 2 times the acceleration times the delta x. Therefore, the acceleration equals the velocity final squared minus the velocity initial squared divided by 2 times the displacement. Velocity final was 3.058 times 10 to the 5th squared minus 0 squared divided by 2 times 0.12. The acceleration.
3.8972 times 10 to the 11.
Times 10 to the 11th?
Yes.
Okay. And so we'll go with 3.90 times 10 to the 11th meters per second squared. The acceleration. Okay, now the force causing this acceleration. We're going to figure out the force causing. Oh, wait. John?
Not mass times acceleration.
We're just going to use Newton's second law. Net force equals mass times acceleration, where both the force and the acceleration are vectors. The only force acting on this is essentially the electric force. Of course, gravity is negligible. The mass of the proton, 1.67 times 10 to the negative 27, multiplied by the acceleration, 3.8972 times 10 to the 11th. The force is
6.50833 times 10 to the negative 16.
with sig fig 6.51 times 10 to the negative 16 newtons. Now we're trying to figure out the magnitude of the electric field for part F. How are we going to figure out the magnitude of the electric field? We did already figure out the electric field. We're doing it again. Jenkins? We know that the electric field by definition is equal to the electric force per unit charge. So 6.50833 times 10 to the negative 16 divided by the charge, 1.60 times 10 to the negative 19. And
4,067.708.
or approximately 4070 volts per meter. Again, exactly what we got before. We just went a different direction to get there. So what we did is we started out by figuring out the electric field, but then we just used the electric potential difference and conservation of energy to figure out the final velocity, to figure out the acceleration, to figure out the net force, to figure out the electric field. So we just went 2 different directions to find the same thing, because we can. Travis,
Was there any way to solve part A without finding electric field?
was there any way to solve for the electric potential difference without first figuring out the electric field? The answer is no. You had to first know the electric field.